In this video, we'll learn about the divergence of a vector function. The gradient has the formal appearance of a vector del multiplying a scalar t. That is, gradient of t equal to x hat dou t by dou x plus y hat dou t by dou y plus z hat dou t by dou z. The term del equal to x hat dou by dou x plus y hat dou by dou y plus z hat dou by dou z is known as the del operator. Del is not a vector in the usual sense. It doesn't mean much until we provide it with a function to act upon. Furthermore, it does not multiply t, rather it is an instruction to differentiate what follows. To be precise, we say that del is a vector operator that acts upon t, not a vector that multiplies t. Now, an ordinary vector A can multiply in three ways. If vector A is multiplied by a scalar A, then it will be vector A times scalar A. A vector A can be multiplied with a vector B via the dot product. So that will be vector A dot vector B. Similarly, if we take the cross product of A with vector B, then it is represented as vector A cross vector B. And correspondingly, there are three ways the operator del can act. If it acts on a scalar function t, then it is known as a gradient. If the operator del acts on a vector function v via the dot product del dot v, then this operation is known as divergence. If it acts on a vector function v via the cross product, then del cross v is known as the curl. We have already discussed the gradient, and in the preceding sections we'll discuss about the divergence and the curl. The divergence. From the definition of del, we construct the divergence as del dot v equal to x hat dou by dou x plus y hat dou by dou y plus z hat dou by dou z dot vx x hat plus vy y hat plus vz z hat. When we take the dot product, we are left with dou vx by dou x plus dou vy by dou y plus dou vz divided by dou z. Observe that the divergence of a vector function v is itself a scalar. We will now discuss about the geometrical interpretation of the divergence. The name divergence is well chosen, for del dot v is a measure of how much the vector v spreads out or diverges from the point in question. Now, the divergence of a vector function is visually represented either by arrows or field lines that point in space. In the arrow approach, the strength of the field is indicated by the length of the arrow as shown in this figure. You can see that at this point the length is large compared to this point. That means that at this point the strength of the field is higher, and at this point the strength is lower. In the field line approach, it is the spacing of the line that tells you the field strength. The closer the lines, the stronger the field. So you can see that the spacing between these two lines is larger compared to these two lines. This indicates that the field strength is lesser here compared to this point. Let's now focus on the arrow approach. In this figure, the arrow is pointing outward and its strength is increasing. From this, we infer that the vector function has a large positive divergence. If the arrow is pointed in, we will say that it has a negative divergence. In this figure, the arrows are all pointed along the same direction and has the same length. For this kind of vector function, the strength at this point and this point are the same. For this reason, it has zero divergence. In this figure, the arrows are all pointed along the same direction, but its lengths are different at here and here. That means that the strength is higher at this point and smaller here. In this case also, there is a positive divergence. In electrostatics, we shall come across positive and negative charges. By convention, electric field lines originate on a positive charge and has a positive divergence. Electric field lines terminate on a negative charge and is said to have a negative divergence or convergence. As an illustrative example, let's consider the Gauss's law in electrostatics. Let's assume that we have a charge distribution ρ in space. It can be positive or negative. This charge distribution produces an electric field E. Let's now assume a closed surface enclosing the charge distribution ρ. Then according to Gauss's law, the flux of that field passing through any closed surface is proportional to the charge density contained within that surface. Or mathematically, del dot E equal to ρ divided by epsilon 0, where epsilon 0 is the permittivity of free space. Obviously, if there are no charges, then del dot E will be equal to 0. So this is known as Gauss's law for electric fields. Let's now try to calculate the divergence of the following vector function. Vector VA equal to x square x hat plus 3x z square y hat minus 2x z z hat. Del dot VA equal to x hat dou by dou x plus y hat dou by dou y plus z hat dou by dou z dot x square x hat plus 3x z square y hat minus 2x z z hat. This is equal to dou by dou x of x square plus dou by dou y of 3x z square minus dou by dou z of 2x z. This is equal to 2x plus 0 minus 2x. This is equal to 0. That indicates that the vector function VA has zero divergence. Let's now calculate the divergence of the vector function defined by VB equal to xy x hat plus 2yz y hat plus 3zx z hat. As usual, del dot VB is equal to x hat dou by dou x plus y hat dou by dou y plus z hat dou by dou z dot xy x hat plus 2yz y hat plus 3zx z hat. This is equal to dou by dou x of xy plus dou by dou y of 2yz plus dou by dou z of 3zx. So this is equal to y plus 2z plus 3x. So the vector function VB has a non-zero divergence.